All right, so Roberto Hernandez is currently a developer extraordinaire at InfernoRed Technology, which is based here in Northern Virginia. He's been architecting and building software solutions using Microsoft and open source technology for the past 18 years. I bet it's 18 years? Is that out of date?
That number keeps creeping up, but yeah, it's somewhere around 18 to 20.
He's been awarded a Microsoft MVP for C# in 2007, 2008, and 2010, and is an active participant in the MVP Reconnect program. Originally from the Dominican Republic, he is a proud father of two beautiful daughters that make his life special. You can track him down on Twitter at Hernandez Robert, or on his blog at overridethis.com. So without further ado, Roberto is going to present on physical computing with .NET Core.
All right. So hopefully at this time everybody's seen my first slide. Acted a bit funky when I was trying to share that my screen with all of you. But yeah, seems like it's going okay. So all right. So like Lee mentioned, my name is Roberto Hernandez, and yeah, I've been around a while in the Northern Virginia area developing applications, mostly in the .NET environment. But like many of you, I mean, I've been curious about uh, the new waves of technology that have come along in the last 20 years. And one of those that's worth mentioning is definitely the Internet of Things, where micro devices actually talk and populate data all over the Internet into the cloud and basically um, produce big data that make our life meaningful in many ways. So um, let me just go ahead and go to my next slide just to tell you guys what you're going to be going through in the presentation. So what we will cover, well, just to get through a bit of minutia, we are going to be doing a bit of an introduction of what is physical computing for those folks that are not familiar with the term, or are familiar with the term in a vaguely way, but want to know for this presentation, what do I mean with physical computing? We are going to be talking about the components of physical computing, specifically um, GPIO hardware components, and we are also going to be talking about uh, currently what .NET Core libraries exist that permits us to interact with GPIO hardware or using other protocols like I2C or SPI managed hardware. And like hopefully, if some of you have been to my presentations before, you know most of my presentations are demos. So that's what's going to be happening at the end. And without further ado, let's move into this, our first slide of what is physical computing. And this is the Wikipedia definition of what is physical computing, but it matches at least the spirit of what I think of physical computing and what I basically do with physical computing, either as a job or as a hobby. So, in general, physical computing is basically the term that describes the designers or DIY hobby projects that basically use controllers, sensors, etc., to basically devise electronic devices such as um, to automate the house or to uh, drive data for an industry. So I'm gonna switch from the screen just for a bit, just to showcase a bit of the hardware that we're gonna be playing with today before going into any deeper in the slides. So this is the second camera that I have hooked up, and hopefully everything goes as expected. So what I actually have for you guys today are two Raspberry Pis that are going to be doing most of the demos. This Raspberry Pi right here is a Raspberry Pi 4, and I don't really have anything connected to it right now. But I do have a couple of projects like this one in this mini pin board that I have on the side, and other that are having more advanced breakout boards like this one. So a lot of the things that we're going to be talking are basically things that we've been doing for the past maybe, I want to say 10 years on the Raspberry Pi environment using Python. And now we're capable of doing it with the .NET Core environment. So let me see, but miss anything? Well, from a hardware perspective, just to be thorough, I am going to be using also an LCD 1602 to present information to you guys during the demos, and I am also going to be using a environment sensor. This one is a AM2302, which I believe is the same thing as a DHT22, that uses a one-wire protocol to provide temperature information to a hardware. So, back to my slides. So I already touched a bit on this on GPIO, but I just want to give a bit of a more concrete explanation. What is a GPIO? So the acronym GPIO basically means a general purpose input and output. And basically, a GPIO is a very generic term because, for example, on the three boards that are on their side on this slide, we have the Raspberry Pi, we have an Arduino Nano, and an Arduino Uno. They all have different versions of GPIO. For the one on the top are merely the naked pins on the top. The same thing on the Nano, and this one has the basically pin ends that are the GPIO input. But this GPIO input are basically just extra that can be managed through the microcontroller to drive different things. Drive LEDs, so the famous blinking light demos that we see all over the internet. Drive motors to maybe build your first robot. Is your intent, or maybe your first drone if you want to drive fancier motors and basically take to the air. So what we're going to be learning today is how to interact with the GPIO inputs in the Raspberry Pi using the .NET Core. And why is that important to us? Well, this group is called Caparia.net, right? So in the past, if we wanted to do that, let's say 15 years ago, before we had the Raspberry Pis, we would probably be programming C using an Arduino Uno or Arduino Nanos, which I think we didn't have at the time. And to us .NET developers, I include myself in the group, C, C++ is a bit of a challenge. So then came the Raspberry Pi about, I think 5 or 6 years later, around 2012, if I recall. And the Raspberry Pi, no, a bit older, maybe 2008. So the Raspberry Pi made things a whole lot easier because now the language that basically you were able to use to drive those pinouts was the Python, at least mostly. You could use C, but most developers, since most of these boards are used for quick prototyping, use Python to get the work done. And while Python is great, I love Python. The problem again with Python was that I had to learn an additional programming language. I had to get my head around it, and I had, which wasn't very hard. But again, it is another programming language from the one I use every day, and sometimes it felt odd. Like I've done presentations at this group, Caparia.net, again, the group that has .NET at the end, combining Python and .NET code, and not that there's anything wrong with that, but again, it felt odd because we are a .NET user group. So, and yes, C# is awesome. That's definitely the plus of why .NET Core and IoT on a Raspberry Pi, if running Windows or running Linux, is great. So, a bit more into what can be done with a GPIO, because that's basically what all the demos are going to be about. With the GPIOs, we can basically turn things on and off. On the Raspberry Pi GPIO board, which is the one that I'm most familiar with, you can actually turn on and off, so binary switches that go from 0 to 3.3 volts. You can also do power modulation. And on the Raspberry Pi, there is no hardware modulation. What do I mean by that? That if we wanted to have, for example, 2.2 volts, we wouldn't be able to tell the hardware to actually produce that for us. So software, using PWM, we can actually, by providing a frequency, we can actually make that a reality. So make the output of the Raspberry Pi be less or more than the full output is by controlling the pinout. In contrast, sorry about that, the Arduino Uno and all the Arduino boards have hardware power pulse width modulation. Lee corrected me on that one. That can be actually done through the hardware. You'll see a lot on the internet this term, and it's actually accurate. Prototyping is something that can be done very quickly on the Raspberry Pi, but once you want to start getting into the precise, getting into using hardware that requires frequencies that are precise, timing that is precise, you'll see a lot of folks drift toward the Arduino landscape, just because those microcontrollers are what they're built for, driving processes and frequency and precision in precision fashion. The Raspberry Pi is more close to a computer with GPIO pins. So, other things that happen with a general purpose input output and the on all devices. So some of the pins in these boards are reserved to be able to speak certain protocols of communication. So SPI and I2C. So one of the things that I think I didn't show on the while I was browsing through here, or if I did, I didn't say it properly. So this Raspberry Pi right here has a device on top of it called a SenseHat. It's very popular for if you're programming on the Raspberry Pi to develop hats that have certain capabilities. This one, for example, has an LED board that's 8x8 that you can use to display information. We'll see some of that later. Has a joystick, has a environmental sensor, a motion sensor, which is right there, that has an accelerometer, gyro, and magnetometer. And I believe that's it. I'm probably missing something, but you guys get the point. There's a lot built into the SenseHat. And the communication with all these devices really happens over I2C. Other devices that I will be showcasing that do similar communication, the LCD 1602 board actually uses can be actually driven over SPI or I2C. In our scenarios, we'll be using I2C to drive the board with the help of a component that's actually already soldered on the back. So, this .NET Core libraries, where are they? How do they come from? So, Microsoft around, it's hard. I don't know if you guys are like me. I've lost total track of time over COVID. I believe it was around 3 or 4 years ago. Produced what were called the system.device.gpio libraries. Now, these libraries are meant to do everything that we had on the previous slide. So, interact with a binary pins on a GPIO, interact with by using those pins using I2C and SPI protocol, etc. And like many things that Microsoft produces today, is a totally open source project. So and we'll dive a little bit deeper into that during the demos. I don't want to go too far in that right now. The other library that's mentioned here on the slide, Iot Dot Device Binding, it's an interesting one. So I did mention that the devices that I was showcasing, for example, the LCD board, the LCD 1602, is a common device that is used a lot when prototyping IoT components. So if we had to basically do that all over again every time we were trying to interact with it, what happens is that we would have a ton of repetitive code, and our applications become messy and hard to develop. So what Microsoft has is a helper library, Iot.Device Bindings, that basically help you out in developing your applications. So the Iot Device Bindings is where I'll find the libraries that will interact with, in my demos, with a buzzer. We'll also interact with that SenseHat using I2C, and with the LCD screen also using I2C. And just for reference, hiding the Mac a bit here. So this is what you will find that repository, .NET/IoT. And this started as a prototype for this general concept. I don't think Microsoft was fully committed to, because at the time, most developers that were doing IoT and wanted to program .NET had a path they could go in, which is installing Windows 10 on a Raspberry Pi and then using .NET to drive the GPIO inputs and outputs. But what happened was a lot of folks, and even the .NET Core platform at the time, was actually drifting to be more of run on Linux. So right now, a lot of the applications we develop on Inferno Red, even though we develop on a Windows environment or a Mac environment, end up being deployed as containers on the Linux stack. So Microsoft started noticing that a lot of folks wanted to basically work with .NET Core and drive GPIO inputs and outputs of build IoT devices in Linux environments, using basically on ARM. And this is what came of it. We two different packages come from here that were mentioned on the slide: the system device.gpio and the IoT device bindings. And just to click around a bit, the device binding list is mostly contributed by open source contributors, so no Microsoft Direct. But like, if I wanted to look at what is available for the LCD matrix that I'm going to be using today, there's that character LCD crystal display. If I click through, there should be a lot more information and samples of usage. And this is pretty close to what we're going to be doing. Another thing you will notice with this library, and if you browse through the samples, a lot of my code will not be like that. And let me just click through and see the samples themselves, is that the code is actually written using and please correct me if I get this wrong, C#10 constructs, which is all the code is actually inline. There's no classes. There's no there's no object-oriented programming. Let's put it this way, because Microsoft decided that in order to try out their functionalities and in order to try out to basically get it closer to what it's offered in a Python environment, they wanted to try this style of development in these libraries themselves. Now, you don't have to follow this style of programming in order to get things done with the libraries. But if you depend on the samples, you'll see that most of them are written that way, so it's good to understand them. So I think that is my last slide. And again, like I mentioned at the beginning, I do not do a lot of slides and code. Now, these are all the demos, and they're basically linear in a way. They will start getting more and more complex. I may freestyle a bit along the way just to get things more concise and more visible. But let's start with the simplest one, the LED, and how to drive it through a .NET Core project, and how does the flow of working with developing an application that way. So the LED is going to be driven by this board right here. I apologize when I insert my arm, my ugly arm, but we'll try to get this going. So this little board basically has an LED, and if you don't want to burn your LEDs, you want to have a 220 ohm resistor on it, and you want to have your negative and positives correct. So I'm just going to go ahead and test it out, because if you ever bought a Raspberry Pi, you've probably seen one of these. And hopefully I get it correctly. There it is. So this is basically the pinouts on the board and what can I do with them. So what are their capabilities? As you can see on the top on this one, it says 3.3 volts or 5 volts. So this type of LEDs, which are pretty cheap, these LED bulbs are going to burn right away if I plug them to 5 volt. So I will have to keep that in mind. And also, as you can see, I also have the feed, the ground, I have GPIOs, and there's two sets of numberings. When I start writing the code, you'll notice that a lot of the configuration when I start writing it is around, am I going to be using logical numbers or am I going to be using board numbers? So the board numbers are just the 1 through 40. They're actually the numbers inside that gray rectangle, or the numbers on the outside, which are the logical numbers for the board. Most of the development happens with the logical numbers. If you look at the samples, they all lose the logical numbers, so that's what we're going to be doing today. And on this board, it's going to be a bit of a pain because I don't have any guidance or whatever. That's why I have that thing handy on the left. But if you notice on the other ones, like I have this nice little breakout into the spreadboard, and if you'll notice, I have all the labels already for the logical board. On this one, again, another type of, this is a hat that basically acts as a breakout board. Let me get that into the screen. So also labeled. So for the demo, we'll be using logical pin 26 over there. I'm going to be using something that requires 5 volts. I believe that is, well, both the LCD screen and the environment sensor, the AM2332. But I also could have used three bulbs, which are available in these two items, or any of the other pinouts. Just by convenience, I ended up there. So let's test out the bulb before everything happens. And this, again, I apologize. This is the only one you're going to be seeing me doing wiring. So negative, negative, and 3.3 bulbs on the top. Let me see. There it is. Yeah. And there. So at least I know that if the demo fails, it's not because the hardware is broken. That makes me very happy. So I'm going to be moving my 3.3 bulbs, and I'm going to be putting it on GPIO 18. Let me go ahead and do that right there. So that's 2 pins down, and it's the next one. So here we are. Make sure that that's in there well. Okay, so that should be fine. Now, into the world of code. So that's my, I'm already in the Raspberry Pi, so let me exit. So I already have the access through SSH to the Raspberry Pi. The way I set up my Raspberry Pis, I gotta admit, I'm a little lazy about it. So I actually enabled BNC access also. So if I wanted to see that Raspberry Pi directly, I could go to it, and here's the Raspberry Pi. I was running something in Chromium before, and if we have time, I think we will come back here and run a demo on this Chromium targeting a API running on the device. But for now, I'll just kill it to avoid bandwidth use. So I'm going to SSH into the Raspberry Pi. This one's my 4B. That's right there. And just to give you a view of what this would have looked like before, I'm just going to go ahead and open a file that I have here. Sorry, this is the projects. There it is. So on the Raspberry Pi, there's this little Python script that I wrote today. All that I'm doing is basically saying, get me access to the GPIO board, set the mode of the board to be BCM. So that's, in this scenario, that's the logical numbering. Set up the pin 18 as we saw in the pinouts. And using that pin, basically loop forever, which some people are going to be doing today. Doesn't happen very often in day-to-day enterprise applications that at least I build. But in building IoT devices, there's a lot of looping forever. just because you're basically running background tasks that are basically waiting for something to happen in order to react. So in this case, we're going to be looping forever and basically setting it to high, waiting for a quarter of a second, setting it to low, etc. So let's see. I'm going to exit. And I'm just going to Python 3 hello GPIO. And here we go. So again, Python works, is great. Probably 75% of the time you're prototyping, it is the preferred language of choice. But if you want to build,
yeah. So, did you want to do? Well, I mean, have you been playing?
Keith, you should mute.
So, welcome, Keith. So again, for us, 75%, probably more, of prototyping IoT devices, Python is going to be enough. If you want to grow a bigger application, a bigger, most robust application, and want to take advantage of building something on the language that you know, so a .NET-based language, C# in this case, .NET Core is the way to go. So I'm just going to go ahead and start that work. So this is still running. Let me kill it. And I apologize, it's going to be on for a little while, because I didn't write a clean way to exit that program. So just to show you a bit of what I already have, because I did build a bit of infrastructure to get this going, so it's not really much. In fact, everything fits here. I just want you to take a quick look at what's happening here. I have an enum that basically has all the demos that are going to be doing, so LED, button, buzzer, RGB LED, and the HD11. And I'm going to probably be going down that path. But what I'm basically going to be doing is going into this main method when this console application is run, checking if an argument is provided. If an argument is not provided, raise an error and return out. If the argument that was passed cannot be converted to a value in that demo type, then raise an error and stop execution again. If I have a valid demo type that I want to and can execute, then I basically go into this process, which is I get a cancellation token source, which I'm going to be passing down to the components I'm going to be building, and I run those components. Now, this task is going to be running. We're going to be waiting for it to end till the user presses any key to exit. At that point, what's going to happen is the token source that I built, we're going to fire the cancel event. So the code that we're going to be writing that's going to be running in this task is going to be aware of the cancellation token, and at that point can clean up resources. That's going to happen in this way right here. And after all resources are cleaned, then we end the application itself. So the first thing, again, LED demo. Oops. Demo type LED. And let's add the break, because that's the thing that I always forget. Now I'm going to write an LED runner that's going to do exactly the same thing that the other app did. And that LED runner class is going to have a run async method that we should await. And that run async is going to take the cancellation token. So let's build that class. So there's my LED runner class, but I'm going to move it to a specific file just to be more clean. And let's rename this variable as LED pin. There we go. Back to the program. Let's implement this run async method. And this is where a pattern starts taking shape. Let me rename this. Oops. So most of the runners that I'm going to be building for the LED, for the HD11, or all the other sensors are going to start in a similar way. I'm going to be running a task, and that task is going to be pass a cancellation token. Now, in here, I'm going to want to have access to the GPIO pins. So first thing I will probably do is go ahead and say new GPIO controller. Now, that class is not currently available to this app, and I did that intentionally because I wanted to highlight that how the libraries depend on each other. So the first one we're going to use is the system.device.gpio right here. And I'm just going to go ahead and add that. We could have easily used the command line for this, but since I'm using Writer, this is a very simple process. And now that we have that, I should be able just to tell, I did Alt Enter there. If you're familiar with ReSharper, that should be like second nature to you guys, system.device.gpio. And now that we have that controller, I can go ahead and say controller open pin, which is basically reserving the pin. Going to be setting the mode that that pin is going to be used in. And in this case, let's just, if I see LED pin, and this is going to be an output pin because I'm going to be producing power through this pin. Now, as before, so as in the Python code, I'm going to be looping forever, but there's going to be a difference in this case. And this can be done in the Python code. It's just more second nature, at least to me, in this side of the world, in the .NET side. So if token is marked for cancellation, then simply step out of the loop. Now, things that I want to do before exiting the loop, I want to close the pin, and I want to dispose of that controller. Your code will probably work fine if you don't dispose or close. I just like to be thorough. So, I guess this is where the turning on the pin basically happens. So write to the LED pin, and what am I going to write? A value of high. Now let's sleep, and I believe this is milliseconds. So let's just do 250, which I think it matches what was on the other side. And same thing, pin value low, and let's sleep again. If I didn't add that second sleep, we wouldn't have noticed that there was actually a blinking action on this demo. So let's see. Everything seems fine. Let me place this in the correct place. So my local machine, I am already in that folder. And let me remove that just to make sure that everything is clean. And let me just go ahead and do .NET Publish. This actually changed a lot from .NET Core 3 all the way to now, because .NET 5 has the concept of portable code. So when I actually am doing a .NET Publish, the code that is getting created is actually going to be able to be picked up from the Mac, or which is my environment that I'm in right now, the Windows environment, or the Linux ARM devices like the Raspberry Pi without really much changes. So I'm just going to go ahead and .NET Publish and just say an Apple folder. Now, if I list what's in that folder, it's just a DLL that is required to be used on the other device and its dependencies. Now, I'm going to go back to that other folder, and this is really where the magic happens. So again, first step, .NET Publish. Second step, I'm actually going to use SSH copy, SCP, to actually recursively copy all the files in that publish folder to the home Pi demo of my 4B. And I'm doing this manual. it doesn't bother me to do it manually, just because it's a very quick prototyping process. So now that this is done, the code is already on the Pi. I will get back to this though in a second and show you guys how to do this not the manual way. So onto the Pi, and now this folder should not be empty. And let's just say IoT basic samples, DLL, and the demo that I have ready is the LED. And hit enter. So switching to the view, and there it is. So I know I wrote a lot of code for this. I'm not gonna say otherwise. But I just want you to consider two things. Like, I wanted to give my code structure and for it to be thread safe and for me to be handling cleanup of my resources as well as possible. But if you look, for example, at the, and I think this is still actually here, at the sample codes, they actually do this straight in a simple method. So, like many things, this could have been done as simple as in the Python side, but you eventually want to add a little bit of complexity just to get things going. So, I did promise one additional thing, right? I promised to show you guys how to do this in a non-manual way, even though the manual way works just fine. But here we are. So this is the same project. Let me just double check that everything I did on that side is here. Here we have same program I was writing. So this is the same thing. New LED, port 18, run a sync. LED runner. So the LED runner doing exactly the same thing. So I wrote a couple of Visual Studio Code tasks with some guidance from the Microsoft Wiki. And let me show you how those look. And you'll notice that there's a reason why knowing the manuals process is so important. So in this case, the first task is a .NET task type process, and everything that's going to happen here, we're going to be running the publish, we're going to be sending it to the output, and where? To that publish folder. So the same thing we were doing before. The second task is a deploy task. So this deploy task, I said that is an SCP, so the same SSH copy, and it's a shell task, and the same command as I had in the terminal. So SSH, SCP, sorry, recursive, from the publish folder all the way out to the home Pi demo. What do I get from building this infrastructure? With this and creating a launch task, in this case, I'm saying use core CLR, request launch. All this information is actually for the Pi. On the Pi, on the home directory, there is a .NET folder. There it is. It matches specifically what it is saying. So I'm saying program.net. And what are the arguments? The arguments is basically the DLL. And the second argument, button. So and we want this to work, let's say LED. Current Windows directory. We said that everything happens in the demo. So, oops. Again, the demo folder was where I deployed this information earlier. And let's see. Well, last part here, the pipe transport. This is the way it's going to be communicating with the Raspberry Pi. It's actually going to be running the application over SSH on the Raspberry Pi. And it did take some setup on the Raspberry Pi. It wasn't too complicated, but I had to run this command to basically install the necessary debugger on the Raspberry Pi for this to work. So back to Visual Studio Code. And the magic of computers. Let's say that we were having a problem here. And let's run this remotely. So the .NET publish happens, same as I was doing manually. Things are built. It's SCP over to the server, same list of files. And now the magic of remote debugging happens. So you can also do this with a Raspberry with Python. I've done it using the SSH debugging features that come, or not, they don't come with it, but with PyCharm from JetBrains. But they're very, very easy to configure using PyCharm. In this case, let's see, goes into my task. This is, I cannot use read the way this is written right now. Just change it for the demo. And I guess here you can see how this basically has some appeal. I just changed a line and I did all the work that I was doing in the command line to build SSH, and now I can debug. And now it's actually in the right place, the right token that I wanted to debug into. So, yeah, magic across devices, across network. It works as expected. Turn that back to key there. I think I haven't committed these two files into the repository, but I will before the end of the night, so that if you guys want to take it for a spin, you would have the option to do debugging and remote troubleshooting of problems using Visual Studio Code. I could have also done this on Writer, but I am not as good as configuring tasks on Writer as I am on Visual Studio Code. All right, so what is going on with my Raspberry Pi? Let me just check that everything's fine. Yep, everything's fine. So I think that concludes the first demo. And just to go back to the slides to keep me honest, so we've done the LED, let's do the button. And I dread this part, but yes, I am going to be wiring more stuff. And my wires are falling apart as I speak, so first thing, put the wires back together. So if you've ever used a button component, I mean, basically what's going to happen here is when I press, the two pins that are on top of this button are basically going to be bridged. So I'm going to go ahead and just put a red one on one of the pins and a yellow one on the second pin. And it's really easy just because this board is so small to get this wrong. Now I'm going to be sending power, so I'm going to be using 3.3 volts from the top here. So there it is, 3.3 volts on the top. Let me make sure that that is correct. Yeah, there it is. And the other thing I'm going to be doing is I'm currently on Gpio 18 for the LED, so I'm going to move 2 down. There's a ground in between to Gpio 23 for the button. So there's my other cable. And let's put it 1 pin out there. So this is what that ended up looking. Yeah, I know, not too visible. It does match the wiring on this board. So the 18 is this white wire that goes out to the LED, and the 23 is the yellow wire that, as you can see, goes out to the button. Now let's see this work. So, like before, let me just add an additional, let's follow the path. So the LED, let's say now we're going to be working with the button. Same thing as before. I'm going to create a button runner that's going to run this test. And just because I know I'm going to need this later, let me just start pulling out things like the LED ping. Let me just do also a button pin. Oops. I'm going to double check my pin. My pin is 23. And on this scenario, I'm just going to say button pin, LED pin, run a sync, and the token source is the token again. For cleanness, let me just put the LED pin also there. And the break that I always forget. A lot of folks are asking about simulators. There are a lot of simulators online, but I think Scott mentioned it. I'm not sure, but I think I have the same opinion, which is the devices are so cheap that it's really worth just getting one or two or three. Like if you're like me, you'll have 5 lying on your desk. But it's just a much different experience working with the hardware. Gives you at least my personal experience, a sense of accomplishment, seeing things work. So they're there, and the run a sync method. And like before, this is basically a very common pattern. We're working with hardware. And here, let's just go ahead and access the controller again. And I mentioned before that logical board, in this case, we are using logical, which is the default. Let's set up the pins. Open pin, let's do both, LED button and the button pin. Set the modes. LED pin, like before, it's just going to be an output. There's the button pin. And this one is an input, but I want to make sure I get the right type of input. So since I'm working with a button, I'm going to say input pull down. And at this point, I'm ready to loop. So this is one style of interacting with a button. There's also a wait for event. So this could be a bit more event driven than loop driven, if you wanted to follow that course. Now, this just to keep this clean, let me write the cancellation code before I forget. And close both pins. And dispose of the controller. And let's make sure that the pin is low. Okay. And now what do I want to happen in the loop? I just want to check if read, we've been using a lot of writes. I think this is the first time we've done a read. If the value coming from the button is high, which means it is push, then let's just go ahead and turn on the LED. Let's write something to the console just to get a visual. And let's write a delay so that this is actually visible for 250 milliseconds. After that, let's just turn off the pin. Looks fine. Not sure why this is red, but let's go ahead and compile this. And send it out to the Pi. And not that. Let's run the button. So let's go ahead. Ooh, nice. I like it when things work on the first try. So very simple demo, but you would be surprised how many times I got this wrong. So there it is. And as we click, let me go back to the console output. You can see that we're also getting those console write lines that we had in there. I guess the reason, again, what I like this approach is that when you're waiting for events, you're going to be flooded with them, and you're going to want to start working with throttles, especially when it comes to buttons. In this scenario, well, I'm basically controlling the time when I'm looking at the button or caring about it. So I don't really have to worry about that. So there. So I think with that, we can say goodbye to my little troublesome little board. And this is actually going to be a simple demo, but this is the board that is actually wired for it. So we're not abusing a lot of the things here. So there we are with a breakout board. So the only thing I wanted to point out here, so it's a bit blurry, but let's just say we have the 18 again going to the LED. We have the 23 going out to the button, but we also now have a buzzard, and the buzzard is going to the 12. This little yellow wire, which is out of the picture there. So what we're going to have to do right now, just to test, it's the simplest of device bindings there is. The buzzard, and we're going to test how to get a tone out of it. So the question that was posted is, do you really need a computer to do I/O control? No, you could use a microcontroller to do it. And in fact, that's where the, I guess, great divide between what an Arduino is and what a Raspberry Pi is in terms of what they can do. The Raspberry Pi, like I said at the beginning, is closer to what a real computer is. In fact, it is a computer. Let's put it that way. It's a computer with a very friendly GPIO ports. But most of the stuff that we're doing right now can be done on microcontrollers that are way cheaper than the hardware we're actually working on. So an Arduino Nano or a clone could go for as low as $5. So yeah, there are things to consider in that regard. So let's go with that buzzard. And like the other demos, let me just go ahead and do that. Drive it off the code that it's here. So buzzard. And let's go ahead and create a new buzzer runner. And this one's going to use add the buzzer pin. But let's also set the button pin and the just the button pin. And run a sync and pass the token. Oops. So like before, let's deploy a task that's actually going to do the work for us, and it's aware of the cancellation token. I am going to set up the button, so I will need a controller. Let's set the pin. And now let's get a buzzer. And again, I intentionally did not include the NuGet package that actually holds this information. So this class. So I'm actually going to go ahead and just do manage NuGet packages again. IoT device bindings. Current version 1.50, and just add it to my project. IoT device buzzer is what is needed. And buzzer pin. And again, let's loop. Let's be aware of our cancellation token. Let's close the pin for the button. And let's dispose of the buzzer. So what we want to do here, let's look at the button again, controller dot, let's see, read button pin if pin value equals high. Then effectively just go in here and do buzzard, play tone. And this should have two parameters, the frequency 440 and the duration. And duration is in milliseconds, so let's do half a second. And let's sleep for 500 milliseconds also. And yes, the buzzer is using PWM. We are going to do another demo of PWM that's a bit more rustic. This one's actually using a device binding that was built using PWM. So I believe this is it. So this is not a very complex demo at all. Let me double check that my program is correct. Looks right. Buzzer and button pin. And buzzer and button pin. Okay, so back to my terminal. Build it. Deploy it. And let's run it. So this one's a bit more awkward because it depends on sound. Hopefully you guys can hear whatever that is. Any raise of hands? No? Nobody? Nobody? Yeah, it's very faint. I gotta spend more money on better buzzers. So, very smooth buzzer, but hey, it works. So, let's see. What is the next demo? So, I guess it's good that we mentioned that we were going to do one with PWM. In this case, we're going to be using PWM to actually run an RGB LED. And I got to be honest, I was kind of surprised that there's not a device binding for an RGB LED. For those of you that haven't seen one or do not know what it is, so this is an RGB LED. It has 4 legs on it. And those 4 legs, 3 of them are the RGB, and this one is, I believe, a common anode, if I said that correctly. And what's going to happen, the common is going to use the negative, so it's in the ground. And the other 2 pins actually receive, through modulation, values that within its frequency are going to change the color on the RGB scale. So let's go ahead. This one's a bit more complex, in terms of code at least. And let's just add an RGB LED runner. This one I'm going to be a bit lazy. I'm not going to name those pins. If I see correctly, let me change screen, sorry, my bad. If I see correctly, and I know it's a bit fuzzy, but the first pin, which would be the R, so it's actually on the 18. The second cable, which is, I guess would be this one right here. It's on the 17, and the last one, it's on the 22, which would be the B in RGB. So that is 18, 17, 22. Oops. And okay, let's just go ahead and R pin, G pin, and B pin. And let's just create a anonymous object, in this case called RGB. And let's say red. And in this case, we're going to be creating a new software PWM channel. And that's going to be on the R pin. So the one thing that I'm missing here is, and this was actually gave me a lot of trouble to get this working, is with PWM, you have to specify the frequency that things are going to happen. I may get this wrong. I may have to double check on the original code. Oh, it's actually half. Okay. So it's 2000. And let's get things started. And for convenience purpose, I'm going to use an anonymous method and call it setColor. I'm going to use a color system.drawing.color. And in this case, what I'm going to do is set the duty cycle that would actually adjust the power that's going into the channel itself. So I'm just going to go ahead and I believe set that. So this is a little bit of a nuisance from the way the color struct is represented. So color.r is a byte. So I'm going to make sure that this is a double on this end. And we want this value that is a byte being represented on a 0 to 1 on base of 255 scale. So let's see. So that is set, and let's just say set it to red. Now let's start the loop. And the due diligence. Let's turn it off. Let's shut everything down. And let's break the execution. So what do I want to happen? While looping, let's do the following. Let's set it to red. So now let's sleep for 250 milliseconds. Set it to green. (200 milliseconds again). And blue. And let's see. Let me give it a second look. Yep, looks fine. So I'm just going to go ahead and do, let's exit that. Build the code again. Deploy it. And run it. So this is the RGB LED. Well, let's go to that screen. Yeah, the colors don't come off as great over the camera, but it is oscillating in a way between what would be red, green, and blue. but on the camera, like green and blue are too similar to actually be noticeable. But, and again, I did say at the beginning that I was actually surprised that Microsoft didn't have a device binding out of the way for RGB LEDs. So the reason I think they didn't do this, if you look for software PWM channels, this is the demo you will find in their documentation. So there's a lot of little that all over the internet in terms of documentation. Sometimes you sacrifice the simplest implementation for documentation purposes. So this is not exactly what they have, but very similar. So I'll just go ahead and turn that off and hopefully it cleans. And let's see what we have next. So, oh, the DHT11. So I'm probably going to combine this two, the DHT11 and LCD1602, just because of time constraints, so that we actually can get to the sense hat a little. So I'm going to go ahead and take this off the Raspberry Pi. And I'm going to bring in this dude. So hopefully you guys can see the characters on the LCD board. We'll just leave it here. And the temperature sensor is going to come through here. So the temperature sensor is using one-wire communication. I don't believe, no, actually, I know that is not either SPI or I2C. So it's a custom implementation in this device binding in order to interpret the environmental data that's coming from this sensor right here. The other device, again, for this demo, just the LCD1602. So a very basic little weather station. So let me go ahead and get that started. And let's do the DHT11 runner. So the device that I'm using is an AEM2302. On the back, if you look at it, it says it's a DHT22, but just because I put DHT11 here, let me just keep with the Joneses. DHT11 runner, there it is. So now that we have that, let's see. And this is another one where it really doesn't matter if I put the pins on the top or not. The thing is, the last demo, it's going to use most of the pins that are actually in place there. So let me just take a quick look at what they have. So here on this breakout board, this one right here all the way at the end, if I can tell, is number, maybe I need a magnifying glass. '26. And actually, the LCD board does not use pins because it's communication over I2C. It's actually an address that is going to be getting from the hardware, 0x27 if I'm correct. And all communication is actually going to go that route. So let's go ahead and create this. That wasn't nice. Let's call this the DHT11 pin. run a sync. And test.run. And pass the cancellation token. So let's get that DHT11 instance. I'll just call it DHT. I believe it would work even with a DHT11 or DHT22. It really doesn't matter. The important part here is that by providing the pin, we're telling the binding that we're actually using single wire communication with the device. So having done that, now we can go in the loop and let's see if this is is expected to get canceled. And let's get the humidity from my sensor as 8%. And let's get the temperature as degrees Fahrenheit. Having done that, what I want to know now is, was the last read action successful? If it was, then why not? Let's just go ahead and write temperature. And we have the Fahrenheit value, make this fixed 2. And we're going to have the humidity also to a fixed 2 number. And this is a percentage. You don't want to be hitting the DHT11 too quickly. So I'm just going to put a delay of 500 seconds. Now this just tests the DHT, but it's well worth running this first and taking a peek and then adding the LCD stuff. So I'm just going to go ahead to my local again, compile. And now that I have it out here, let's just go ahead and do DHT11. I should have, well, I am getting information, but I should have put where it failed. I gotta be honest, it fails a lot. And it's one of the, it's a well-known issue. If you go to the Iot Dot Device Bindings repository in GitHub, these devices are not too reliable. They work, if you're using the Python libraries, around 90% of the time. If you're using this library, maybe around 75% of the time. And it's all about timing. If you want it to be 100% precise, I believe the common comment that I've seen is use an Arduino. So that being said, there's a value in this data. It's just not that reliable to the nanosecond. So I have the data. Let me stop that from executing. We add the DHT11 here. And let's build up that LCD. And I'm not going to type the LCD code without copy pasting it. It's just too complex. So let me go to the LCD runner demo that I had here and copy paste that. I can, however, in this scenario, walk you through what's basically happening. So we have the I2C device that we're basically going to be communicating with. And this I2C device on the documentation of the LCD 1602 actually says that it's going to be using the 0x27 address. And this is because it is using this chip, this PCF 8574 driver. If we look at the camera, what I'm referring to is this black chip that's actually already soldered in place there. It is so well soldered because I didn't solder it. I actually bought the piece with the chip soldered already in place. So a lot of the information that's actually on those 3 or 4 lines of code come from the documentation of this PFC driver. And the only cables that go out, it's 5 volts and a ground. And the if I bring this here, because I'm going to botch the pronunciation, the SOA and SCL actually I2C pinouts that the Raspberry Pi has. So let me turn this around. Looks like it's going to be backwards, but it's okay. So again, all of this actually comes from the documentation of the PFC 8574 and how it's being used. And the address also comes as part of the documentation of the PCF 8574 board. Now, at this point, we're ready to, let's say, if a redex is successful, let's do this. Oops. Didn't I give it a nice name? Yep, LCD. So LCD, set cursor position, 0, 0, that's a top left. LCD, right. I'm gonna steal this, we're gonna have to do a lot of editing. Just that. I2C is a protocol for communication supported by the Raspberry Pi and all microcontrollers, to be fair. It allows to control complex devices through a ton less number of pins, since everything is going across a limited number of wires up and down. Sure. So at that point, first line, temperature, second line, the time of the day, things that I want to do. Let's do when we're done, starting the backlight off, which is not off right now. I kind of wish it did that by default. And clear it. I guess it doesn't matter. Okay, so that's it. In this case, we have the device that's communicating over I2C protocol using that PCF driver. Very common scenario for LCD 1602s. Practically all IoT devices that are out there have an LCD 1602 and provide information when they're physically visible. So if everything's right in here in the program, and if I got that pin correctly, if not, I'll get my magnifying glass. Although it is the same here, so might as well check. Let's see, basic samples, DHT, Led Runner, and the pin that I have here. It's 20CJ. I'm not losing my eyesight so much. Let's build this. Let's copy it out. Interesting, and this is not really this presentation comment, but in general, how .NET has gotten so efficient of only deploying what it needs out to the client. So in this scenario, as we've added other things, it's definitely become a beefier copy, but it's still not 400 megabytes of an SDK going across the wire. So I'll go ahead and run that, and again, DHT11, and probably best if I go here, And wow, I thought that was going to be backwards. Probably backwards for you guys. And that I can control. But as you can see, we have the temperature, we have the humidity, and we have the time update. It is very bright. So going back to a comment I made earlier, so yes, you can do this with microcontrollers. If you're a programmer, though, my experience has been that when you have this, and this is obviously a very simple prototype, and then you want to basically include your data as part of any type of major data consumer in the cloud. So let it be Azure, let it be AWS, any type of IoT, data aggregator. Then it's when it starts getting a bit more complex. So there are obviously the .NET SDKs that are very powerful to interact with the Azure cloud. And again, also for AWS, and the same thing can be said from Python. The interacting with the cloud, though, from a more low-level language is a bit more interesting. So glad that that one worked. Let me see what we have left. So this demo, I basically put together two things: the DHT11, which was using a device binding, and it's a very specific device binding. In one of my earlier slides, I mentioned protocols of communications to GPIO ports, I2C, which is what the LCD1602 was using, or the DHT11. Now, before I dive into the HAD, I do want to show what would be, let me see, a more complex demo. And this one is meant to be used with GitHub Actions, but the setup is a bit insane. That's why I keep it simple for the presentation. So I do have that code for you to see, but in terms of hardware, let me explain what would happen. So when a build is queued on a GitHub action, it will send through a webhook to my local IoT device. So very simple interface, a JSON package, and that JSON package is used to display information on the LED light and information on the screen on is a building process, is a build completing, etc. There's a question of what is interfering with the timer. It's just in this scenario, all the different resources that take to run a computer rather than a microcontroller that's just focused on that. So let's jump right into visualizing this. And I already have the code loaded here. To be fair, when I started writing this presentation, and I think I did that maybe 10 months ago or 13 months ago, in that range, I started writing this demo that was very complex. And I realized at some point that I had overdone it. So I basically took a step back and let me close this out. And I basically took a step back and said, in order to showcase the things that need to be showcased, I don't have to build such a complex application. So in this scenario, what's in here, though, just so that we can basically see it in action, there's an API. It's basically an ASP.NET Core API running .NET 5. And the only thing that it has is a controller, and that controller takes in the webhook from GitHub. I'm not going to be hooking it to GitHub. I'm going to be actually passing values using curl, Postman, or in this case, Swagger, directly into the hooks. So what happens when this hooks gets hit? The hardware runner, this thing, iBunner hardware runner, gets basically passed the run information from the GitHub action, and it's actually parsed to be displayed in the hardware itself. So if I probably do right-click, go to implementation, you will see that I have this class called monitor hardware runner. And in this monitor hardware runner, I have an extraction for a button, an extraction for a buzzer, extraction for an LCD, and extraction for an LED. All these things are actually, from the point of view of code, if not exactly, very similar to what I just wrote for you guys. In this scenario, though, this monitor hardware runner is basically using that in a more complex way. It's basically taking in the run information from GitHub and basically going through the task and saying, hey, if GitHub says it's a failure, run failed. And what would a run failed scenario look like? A run failed, oops. Well, that took me nowhere. But here it is. So basically, we would write on the LCD failed, we would write the time, and we would turn on the LED, so the button would show up. If the build is actually queued, then what we actually do is we say the build is queued and basically turn on the LED and in a not enough blinking fashion completed. And if it's completed, in this case, we just turn off the LCD and display that the LCD is working. The buzzer is actually used here or there just to beep, to be a notification when things happen. So I'm going to go ahead and, from a hardware perspective, get this ready. Shouldn't take long. Also, getting this out. Can't guarantee that as I remove that, my whole hardware didn't reboot. But here we are. And let me get the jumper cables. And that. Oops. That should be enough. So again, the LCD board and a lot of the components we just saw before. One quick look over the wires doesn't give me anything to be concerned about. So let's go ahead. And I actually have all this code already on the Pi. I compiled it early and pushed it out there. So on the Pi, on my projects folder, I have a build monitor, which is exactly what I need. Again, to my earlier comment of pushing out a very efficient assemblies out there. So there are the Schwab vocal assemblies that will actually provide the swagger for my API. So I'll just go ahead and .NET the DLL, which is in this scenario is Iot Dot Net Core build monitor API.dll. And there we are. So obviously this is only available on localhost. One of the things I would recommend if you guys want to try this for real, as in hooked in with GitHub and all, is use a tool such as in Grok to actually port forward those local ports and make them available in the internet. So now that this is running, let me go back to the BNC viewer that I had on earlier. This doesn't like to be too efficient when I'm sharing screen. But as you can see, let me see if I can get a better, yeah, hopefully that doesn't move. But as you can see, basically we have a status completed and really doesn't matter anything else for the demo purposes. If I click execute, this is gonna be posted out to the API. That's a good sign. And it's probably better if I just do this. So yeah, the text is backward. But as you guys can see, it says completed and it gives you a specific time. Now, we did say that there were other scenarios. So if I, for example, in this scenario, go ahead and say failed, I believe that that will trigger failure. And apparently I was wrong. Is failure, let me double check. Go to declaration, failure. Sorry about that. And there we have a failed. And the red button. So again, I just wanted to show you how all those little classes that I actually built came into the world. And again, when I was in the process of writing this and getting some material out there, I started writing this application to build a build monitor and had all those little parts. But in the course of what will be, let's say, 2 hours on a user group, which is what probably a little bit more than what we usually get, or on a code camp, which is usually 45 minutes, it's really hard to go through all that code. So I decided to strip it down and basically just show interactions with the GPIO directly. Now, it is 8:27. We can do a bit of the demo for the Sense Hat. Let me just get that up as quickly as possible. And basically what that means is I'm going to get one Raspberry Pi out of the way and just put this one in. And the Sense Hat, if you guys don't know what it is a hat that was actually developed for the Raspberry Pi for it to be sent into outer space. Well, not outer space, to be placed in orbit. And if you look for it on the internet, you'll find reference to AstroPi, which was the original name that it had, because it was basically a contest where high school students and college students all over the EU actually wrote code that was guaranteed to run and gather data on the space station for X number of minutes. So I'm just going to write some code to drive this. Nothing complex. I just want to show you guys that we can use this an I2C device and actually just pass some information to the matrix. So let's see what I have here. And I am going to do this as quickly as possible. I'm just going to steal a little what we have here. So I'm going to steal this program class. And remove a ton of things. For the Raspberry Pi and the Sense Hat, we don't really need to know the pin numbers. Again, it's an I2C device, so it's going to run through through the SCL SOA ports, and all the devices that are on top of it is going to work. So let me put a bit more speed into this. Or not. I like it when the boats go my way. Okay. So here we are at the same place we've been a lot of times. We have a task that's going to run that's going to interact with the hardware. Now, again, I'm trying to keep this as simple as possible, so I'll just copy paste this from the code that I already wrote. And here we are. So I do need to bring that in, bring system.drawing in, and there we are. So let me just walk through this real quick. So what we have now, we're basically getting an instance of a SenseHat. We don't need to think about it a lot. This is just an I2C device, so we're just saying, get me to the SenseHat. I'm creating an array of colors that I'm going to iterate through. For the first time, I'm going to say fill it to white, but after that, it's going to iterate through red, green, and blue. And looping forever again. For each of the colors in that array, I'm going to fill it up. And just because the hat can do other things, I am going to read the temperature from the hat and the humidity and just output it to the console. So this giving me an error here because I don't need any of this. And what else? This can be removed. This can be removed. And this can be removed. So, okay, so at this point, I think we're completely ready. So I'm going to just go ahead and build this in my local. Same cycle I've been doing as before. So .NET publish output to folder called publish. Run folder. All right, and the file expected. And let's SCP this, but we're going to SCP instead of the Raspberry Pi 4 that I had connected, this is a 3B. Already there, I already SSH into that machine. So here I should have all that I need to run, and rpi senshat.runner.dll. Now, temperature and humidity are working. Now let's just see if this is actually working. So yeah. Now, again, if you guys want to start playing with a Raspberry Pi and want to go, it's not low budget, but you want to go and have a hat that has a lot of the components you will need, like, again, joystick, environmental sensors, motion sensors, and a nice little LED to play with, I'd recommend you buy this SenseHat. And there are very good libraries for it in Python and in .NET Core. So I believe that's it. Let me check my slides. So yeah, this going back to this slide, which is basically my guide, the last demo that I had in store with SenseHat, I did have this architecture diagram, very high level, of how the data flows from the GitHub into the application that I built. There is no man in the middle in this flow, and I mean that in a good way, not in the hacky way. Just because I didn't want to involve any cloud mechanisms in the transmission of data from the webhook all the way down to the device. But that's one of the things that can benefit you if you're using a language such as .NET Core, which is .NET, sorry, C#, and the SDKs that comes with it. Now, I believe that's it. Yep, the end. And all the code that I showed, some of it is lacks documentation. By that, what I mean is a good README, but everything you're actually going to find here in the github.com/overwrite this. So please feel free to hit me on Twitter and download the code, send me complaints if it doesn't work. I am I will be glad to help you out. And thank you very much, guys, for attending.
Yay! Thank you, Roberto. That was awesome. What a fantastic presentation.
Thanks.
I love physical computing.